Hi everyone, this is Kat Rayburn,
B. Jones.
and this is our project 2 for fluids. So we're first going to click on Fluid Flow Fluent. We're going to right click on geometry, make sure that we're in 2D space, and then we are going to right click again. Make sure you select New Modeler Geometry. It's going to take a few seconds to load, um, but once it does, we are going to click on Z so we can be in the XY plane. We're going to sketch a rectangle. It does not matter where you start from because we're going to change the dimensions. So for our dimensions, we're going to change horizontal to 1 meter. Make sure you click on both sides so you can get the dimension out. We're going to change that to 1 meter. And then for vertical, we're going to hit the top and the bottom. And then we are going to make it 0.1 meters or 10 centimeters. Then we are going to click on concept, surfaces from sketches. You're going to select a box. We're going to select it, box, generate. And then we're going to scroll in and you see our tiny gray box means it is working. And now we are going to see how there is a green check mark. That means everything is good. So now we're going to go into mesh. Going to double click on mesh. There's nothing we need to change. We're going to wait for it to load. It is still loading, but once it loads up, we are going to click on Z. So we are in the XY plane. And then we have our body here. We're going to click on mesh. We're going to go ahead and generate a mesh because we want to show how it begins. So this mesh is It is there, but it is not enough. We need more. So we're going to click on the full face. We're going to do a face meshing. And this face meshing is going to straighten up the lines from the other one and see how they are straighter lines from the original mesh. That is good. We need more. So we're going to click on our edge. We're going to click on the top and we are going to create a name. This name is going to be far field pressure. Okay. And then we're going to have the left be our inlet. So we're going to click on that. We're going to create name. We're going to do inlet. And then our right is going to be outlet. Very good. And then our bottom is going to be our flat plate. And then we're going to collect the face and we're going to make that air. We're going to name it air. This is going to be our reference body. Okay. And once you have all of those name selections, we're going to make further meshes. We're going to insert, we're going to size, we're going to control click the top. We're going to control click the top edge. Make sure we're in the edge selector and we're going to hit apply. And then we want our element size to actually be number of divisions. We want number of divisions to be 50. And then we're going to say no to capture curvature. And we're going to change the behavior from soft to hard. Then we're going to generate, and that's going to generate a little more boxes. And now we have smaller and a greater number of boxes. This is good. We want more. So we're going to hit insert again, sizing. We're going to click on the inlet. We want to apply. We're going to do element size, number of divisions again. We're going to do 60 this time. We want a little more. We're going to capture curvature, no. Hard behavior. Our bias type, we're going to select the first option. And then we're going to define that as 70. All right. And we're going to hit generate. And then it should show a concentrated area. And that is good. So we're going to hit mesh again. We're going to do the other side. We're going to do the outlet. We're going to select the outlet, do the same thing we did on the other side where we're going to do number of divisions, 60, and then we're going to change our capture curvature to no, and we're going to do our behavior as hard. Our bias is going to be the first option. This one is different. We're going to do 70, but we're going to make sure reverse bias is applied so that it doesn't focus on the far field pressure. Instead, it focuses on the flat plate. All right, then we're going to generate, and it should make a concentrated flat plate area, as we can see down there. All right, let's move on to the next step. All right, now we can see that we have a little lightning bolt. We're just going to update it, and then it should turn into a green check mark. And afterwards, we're going to go for the setup. And then once we're loaded in, we're going to now hit setup. We're going to do, instead of single precision, double precision. We're going to double click into setup. We're already in double precision, so there's nothing we need to do on this one. We're just going to hit start. All right. We can see our little, while we're still waiting for load, we can see our little green area. That means it's going good. We're going to click on models. We're going to we're going to hit viscous. We want to make sure it's a laminar flow. So we're going to hit laminar. All right. And then we're going to go into materials, make sure our fluid material is air. And for air, we're going to change some things. We're going to make it 1.2 density and 1.8 times 10 to the negative 5 for our viscosity. And once we did that, we're going to change and create, close, and we're good to go. And then we're going to go to our cell zone conditions. All right, we're going to make fluid, make sure it's changed to air. That means everything's good. Awesome. Now let's go to our boundary conditions. We're going to change a little thing about each of them. We're going to go inlet velocity. It's good that it's a velocity inlet already. We want that. We're going to change our velocity to 2. We're going to apply, close, and then move on to far field pressure. Now this one, we are going to make sure that it is good. Everything here is good. Internal, we just want to make sure it's set to interior air. There's not much to do there. Outlet. Our outlet, we want to prevent reverse flow. For our wall, we are just going to make sure it's stationary and no slip. Good, it's already that. Let's close. Let's go to reference values. So our reference values didn't update, so we're going to go ahead and change them here too. We want 1.2, 2, and 1.8 times 10 to the negative 5. And that should be it for what we have to fix. Compute, we want to compute from the inlet, and our reference zone should be air. All right, and now we're going to go into initialization. We want a standard initialization. We're going to compute from the inlet. Everything else is good, updated, initialize. All right, and we're going to take a couple minutes for it to initialize. We're going to hit it again because the error popped up, but that error is okay. We're going to change the number of iterations to a lot of iterations. We want a lot of data. So then we're going to hit calculate after that. The calculation is complete. So we're going to get out of this. We're going to check on our residuals. All right, and we're going to go to the next step. And yes, we're going to quit this application. And now we have our green check marks, so we're going to go to results. And once we double click and wait for that to load, we get our little image. We're going to hit Z, so we're in that XY. We can see that image front facing. We're going to add a line. This is going to be our X35 line. And then we are going to make sure that the point is on the bottom and the top. So we have 0.35 is where it is, but we want the second one to be 0.1. It's going to be our top point. Samples, we want 100 samples. We're going to add another line. You see our little yellow line over there. This one's going to be X75. We're going to make sure that is at 0.75 for both X coordinates. And then for the second one, we want it to be 0.1 for our height. 100 samples again, apply. And now we're going to have a little yellow line over there. All right, and then we're going to go to our contour. We're going to make the contour is going to be symmetry 2. Going to make it a velocity U. Global, we're going to make 110 contours. All right, now that is what it is going to look like. We see that it looks all right because the area, the flat plate is close to blue. It's all centered on that. You can see that the higher velocities are above the flat plate. That is good. All right, now we are going to make a chart. This is our chart. Going to make it a velocity chart. Going to choose a data series. I'm going to call it 35 centimeters. I'm going to choose X35 as our reference. We're going to make another one. This is going to be the 75 one. 75 centimeters, 75. So our velocity axis is going to be velocity, and then our y-axis is going to be y. And we're going to hit apply. And we have our velocity profile. All right, and then we're going to add a line again. We're going to make it 100. Make that at 0.999. So we're going to have it just below the height so we can get our line. All right, we're going to change our first point to be just above the flat plate and then just to the right of the flat plate. And then our point 2 is going to be just below the height. So we just wanted so we're going to make a line. And then we are going to make the line go straight across. So we're going to have a 0.99. So it is just above. Then we are going to going to exit out of this area and we're going to go into results. See how we have all of our nice check marks going into solutions now? We just came from results. Now that we are here, we are in solutions and everything appears to be working in order. We're going to make a plot. We're going to do an XY plot. We're going to make this the wall fluxes part or wall shear stress, and we're going to have it calculate the plate. If we move it to the side, everything looks good. Our wall shear stress plot looks good.
Usually we would write to file and then you would put it into Excel so you can graph it with a theoretical, but we already did that. So we're not going to do that again.
We will show those data at the end. All right, we're going to do another plot. We're doing another wall, except this time it's skin friction coefficient. We're doing this from the plate. You want to see what that looks like. And that looks good. Write it to file, it's submitted to Excel, and we make a graph out of it. We're going to compare it to theoretical values. So then we go to reports, forces. We are going to click on plate. Then we're going to save output parameters. That looks good. So then we're going to close. We're going to report our definitions. So let's go into report definitions. I am getting a slight error notification, but that is okay because it appeared anyways. So now we are going to get our force report. We're going to get our drag. This is our drag coefficient. We're going to do it relative to the plate. And we're going to hit OK. And get our report. Selected the incorrect one, but that is okay because we're just going to go back in and we're hit drag, plate, compute, and that is our drag coefficient calculated from Ansys. All right. Now these are our Excel graphs. You can see the values. There's a lot on the side, but you don't need to worry about those. This is just our wall shear graph compared to our theoretical values. You can see that also the skin friction coefficient graph, you can see that the simulated data is in blue and the theoretical one is in orange. So they do start off at different points, but they end up at the same one, which means that our theoretical data and our simulated one matches. Same for the wall shear. And then for our theoretical coefficient and our drag coefficient. All right, so our calculated boundary thickness from the simulation and our theoretical boundary thickness, there is they are similar, although the one from the simulation is more accurate because it is a simulation and there is always human error in calculations. So take those into account. They are very similar. All right, and we have our drag fluent from the fluent and from the theoretical calculations. They're also similar. Okay, and that we have misplaced something. We must go back to results. And now that we are back in results, we are going to do another contour, and this is going to be our pressure contour. This is going to be our pressure contour. And doing this is important because we want to make sure that we have 110, and it's important because knowing where the pressure is going to inform us on where the central point is, and that is our highest pressure, which is right at the beginning of the inlet and right on the flat plate, which means that our simulation is. And that is everything. This has been Project 2 by Kat and
Phoebe.
thank you for watching. I need to go home.